In 3.2b, we are going to be looking at the graphs of quadratics. So we're going to start doing quadratics that are in this form. And I call that vertex form because we can clearly see where the center vertex of our parabola is. It's going to be at HK. Now you'll notice H here in the formula, it's the opposite of H. So that one changes sign, but this one does not, okay? Now the best way to graph a parabola is if we know what that H is, we need 2 points above it and 2 points below it at the very max, okay? So if we have this function in this form, if you don't see anything with the x, if it just says x squared, then we can just plug in 0. So it becomes very nice. The vertex would be at 0. So we're going to plug in 0. We're going to plug in a few below it and a few points above that point. So that's your vertex. So if we want to graph h of x equals x squared, just make sure that when you're putting in that number, when you square it, it is going to become a positive. So -2, that quantity squared is 4. -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. And let's graph our parabola. So that is graphing example 1. Now that is our parent function, so that shouldn't have been much of a surprise as to what happened. But now let's look at one where we have something happened to the function. So we still notice that there is nothing with our x. So we can technically say that our h is 0. So let me write it just a little bit bigger so we have it. So our vertex, the h value is 0. Now we know that because there's nothing inside of the squared that would change that. So let's plug in some values below it. -1 and -2 will work. +1 and +2 will work. Now, when we use this function, be careful. We are going to square it first, and then we are going to do anything outside the function. So we're going to get -2 times the quantity of -2 squared plus 4. Now that's going to become a 4 before we multiply it by -2. So we're going to get -8 plus 4, which is -4. Now, parabolas, quadratics, they have symmetry. So we should see some good things happen, and I'll show you what to look for in a minute. But if we plug in -1, we're going to get -2 times -1 squared, which is -2 times 1, or -2 plus 4 is 2. If we plug in 0, we should get -2 times 0 plus 4, which is 4. Now we should see a symmetry happening. So if we plug in 1, because it is equidistant from the vertex, these should have the same value. So I'm expecting to get a value of 2. So I get -2 times 1 squared plus 4, which is -2 plus 4, or indeed 2. And if I plug in 2, I'm expecting to get an answer of -4. Which is -8 plus 4, or guess what? -4. So if you have chosen the correct vertex for a parabola, the two x values you plug in right next to it, equal from distance away from the vertex, should match. And then equidistant again should match. And that should keep going on and on like that forever and ever. So let's actually plot our points. So at -2, we're at -4. At -1, we're at 2. At 0, we're at 4. At +1, we're at 2. And at +2, we're also at -4. So we should expect a parabola. There should be symmetry around the vertex. So there is a line of symmetry right down the center of that parabola. The negative in front flips it upside down, and this 4's job is to actually move it up 4, and this 2 kind of stretched it a little. And we're going to be exploring what we should see as far as any changes made to the function. What should we expect to happen? Now, this is your 3-2B homework. Let's talk about that for a minute. For problem 1 and 2, your vertex is at 0. So just plug in 2 points below it and 2 points above it. So -1, -2, +1, and +2, and you'll be able to find what you want. Now I want to talk about the ones at the bottom, 7 and 8. Whatever is inside the square, so here x minus 3 and here x minus 4, you're going to set those equal to 0. That is going to be your h. That is going to be our vertex. So for this one, our vertex is at 3. So we're going to plug in 2 points below that. So why not 2 and 1, and 2 points above that, 4 and 5, and just follow order of operations. Now here, if we set x minus 4 equal to 0, you're going to get a value for the vertex at 4. So again, always just, if you know the vertex, plug that in, plug in 2 points below it, 2 points above it, you got it. So those are some quadratics. And now if we could please move on to 3.3a. It's a very quick one. You'll see there's only 2 examples. Let's do that. So in 3.3a, we're going to be talking about the average rate of change. In a calculus class, we are going to talk about slope as being an average rate of change. So you know we've got our slope. That delta symbol in mathematics, that's a delta. And in science and in math, delta refers in a change in something. So this is really just our change in y over our change in x. So if we use the standard notation of slope from back in Algebra 1, y2 minus y1 over x2 minus x1, that's okay. We are going to use function notation quite often. So you'll notice this is just the y that goes with x2. This is just the y that goes with x1. So it's just y2 minus y1 over x2 minus x1, but a fancier way to put it in function notation. So that formula is just slope, but if you ever see something said find the average rate of change, they just want the slope between those 2 points on the graph. So let's look at our first example. In this first example here, it says find the average rate of change of a function given its graph. So we want to use the graph of the function to find its average rate of change from 2 to 5. So we're just going to look at an x value of 2. Let's I don't know. They don't even have values of 2 and 5 on my graph. So we're going to put some on there. Okay. So assuming they had the points in the correct location, we would find the point at 2, and I would probably label that. That is the point 2, 1. So assume there was a point there. And assume there was a point at 5, 3. And so whatever those points are on the graph, whether it's a discrete graph like this with just points on it, or whether it's a graph with a function, you just find the points at x equal 2 and x equal 5. and then you do the slope between them. Now it's customary to call the left one x1, y1 and the rightmost point x2, y2, but you don't have to, just as long as you're consistent. And we're going to go 3 minus 1 over 5 minus 2. So the average rate of change between 2 and 5, once we find the points, label them, and do the slope, is 2 over 3. And if it's a fraction, just reduce it as much as possible. Let's do one more. Now, if you have the graph, you can use the 2 points along the graph. If you think about if the line connected them had a slope, what would the slope be? But if they give you an equation instead, what we want to do is we want to find f of 2 and f of 3. Well, 2, if it does not give you a graph, but it gives you a function and wants you to find the average rate of change, our first x value, we're going to call that x1, and this one is going to be x2. We're going to plug in x1, so we're going to plug in 2 into our function, which is 8 minus 8 plus 6, or 6, so that is the 0.26. And then you got to plug in your second function, or your second value into your function, so we're going to plug in 3, which gives us 27 minus 18 plus 9, which is 18. So that is the 0.318. Now, as soon as you have your 2 points, we are going to use the slope formula. So, you can label these x1, y1, and x2, y2. It's traditional to use the smallest one as your x1 and the larger one as your x2. So our slope is going to be 18 minus 6 over 3 minus 2. So if you were to graph this function and connect those 2 points, the slope of the line that connects them would be 12 over 1, or 12.